Welcome to the Polar Steam Cool Connections live stream. While we are waiting for folks to join, please post in the chat where you are watching from. And if others are joining you, perhaps from a summer camp or library viewing, we'd love to know how many people are watching from your location. We are going to get started as you post that information in the chat. I'm Jamie Ivory, the logistics coordinator for the Polar Steam program, and we are excited to have you with us today. Polar Steam is a US NSF-funded program based at Oregon State University that facilitates virtual and field-based collaborations between polar researchers, educators, and artists to enhance science communication, bringing polar science to everyone. A recording of this live stream will be posted on our YouTube channel. We will keep the focus of today's event on this team's stories and experiences, understanding the drivers of saltwater intrusion along the Arctic coastline. However, I will mention that we are very excited to share the 2026-27 Antarctic artists and writers have been selected. You can find those fellows and their bios on our website. While applications for the Polar Steam Antarctic Artists and Writers Program and the Educator Program for the 2027 and 2027-28 season has closed, we are still looking for NSF-funded polar researchers that want to collaborate with an educator or artist in 2027. And we'd also like to invite you to come join us at the Polar STEAM Summit. This is where polar science, art, and education will intersect and curiosity will come to life. This is an in-person event held in Corvallis, Oregon, October 1st through the 3rd. We'd love to have you join us to strengthen your broader impacts and science communication skills, to share your work in creative and engaging ways, and to build meaningful networks. All right, now we'll focus on today's event. Today, we're excited to connect with two of our Polar STEAM Fellows, Julia Guimond and Lauren Cursiers, taking a short break from fieldwork to join us all today. They are live from Prudhoe Bay, Alaska, at the very top of Alaska. You can see here with that black marker. We will start with a presentation from the fellows and follow that with questions from all of you, our viewers. You can submit your questions live in the chat. Our team will monitor those questions and the questions will be submitted and any questions that were submitted ahead of time. I'd like to introduce our fellows. We have Julia Guimond. She's a groundwater hydrologist studying coastal groundwater dynamics along temperate and Arctic coastlines from Woods Hole Oceanographic Institute. And we have Lauren Cursiers. She's a middle school teacher at Manville School District, specializing in environmental science, committed to cross-curricular science education as a pathway to authentic, meaningful learning. Julia, Lauren, welcome. I'm going to go ahead and turn it over to you to tell us about your experience studying saltwater intrusion effects on permafrost landscapes.
Awesome. Thanks for the introduction, Jamie. Can everyone hear us and see us, hopefully? This awkward angle.
Yes, we can hear
All
you
right,
perfectly.
awesome. Hi, everyone. I'm Julia Guimond, as Jamie already said. And so we are here in Prudhoe Bay, Alaska. We just ended our 2-hour truck ride from the beautiful location of Dead Horse, Alaska, out to our field site. So I'll give you a bit of a quick tour. We had hoped for a sunny day. It was supposed to be a sunny day, but instead it is a pretty calm and buggy day out here and a little colder than we had hoped. So this is a project that we're studying the impacts of saltwater intrusion on the tundra. What is saltwater intrusion? So if, classically terrestrial ecosystems run on fresh water, that's what the vegetation likes, it thrives on, the chemical reactions rely on. But sometimes The ocean rises higher than usual and it pushes all that salty ocean water into these freshwater environments, changing the landscape. And that is the phenomenon that we're studying. That's the field team. We'll hear from each of them in a second. So to give you a quick little tour before we dive into everything. This is the Arctic tundra. Please ignore the oil field infrastructure in the background. We rely on this infrastructure to actually drive to this field site. But what we're looking at here is relatively healthy tundra. So you walk anywhere really along the coastal plain, you see this green vegetation. What you might be able to see is this polygonal tundra here. So there's the center of a polygon and the troughs. And now as we turn and look out to which borders Arctic Ocean, we see a transect from this really healthy tundra. This is all rack lines, so we know that the ocean has at one point come up this far. And as we walk out towards the ocean, you see less green vegetation, also more of our instrumentation. And eventually we enter what is a very degraded zone. So we call these different sites, this is Mordor, as you can see. I call it the elephant graveyard. There's no vegetation, not much living out here. It has been incredibly impacted by the influence of salt. So this area once looked like this area that we just came from. And so to understand what's happening, we're really coming at this question from a number of different angles. We're studying
So, I just wanted to cut in here for a
different
second,
areas,
Julia.
both in terms of, oops,
Julia, it's a little pixelated. So, you talked
okay,
about the two sites and how they're looking different. So from the pixelated view, this is looking less pixelated now, but it looked like
okay.
it looked like there was a lot of like debris, like wood debris, and then a lot of maybe like mud and dirt. Could you maybe just like describe the
Yeah,
differences that we should be seeing just to make sure we can get a good idea?
sure. Sorry. Uh, most satellites are down today, so we're running on a little low service. So what we're looking at right now uh, is an area that has been affected by saltwater inundation. So this ocean water's come up and there's the vegetation has been killed off. You can see that a lot of sediment and rock has been deposited on top of these polygons. And that is in contrast to the healthier, greener vegetation that I've now turned the camera and we're looking at. Um, and so, yeah, okay. So I'm going to pass it over to Lauren, who's been joining us out in the fields this past week, and hand it off to her.
Hi, everybody. So we got here a couple of days ago, and one of the first things that I noticed is that there's a lot of similarities from what's going on here in the Arctic to what I've seen in New Jersey. There's quite a long journey from New Jersey to Prudhoe Bay. But while we're seeing all these different changes in the Arctic, we're seeing these changes, back at home too. So the connections are definitely prevalent. In New Jersey, we have a lot of problems with storm surge, and all of the salt that's coming in is changing the dynamic of the coastline, changing it from coastal wetlands, freshwater wetlands to saltwater marshes. So we're seeing a lot of similarities in the tundra to, back at home. So it's one of the very first things that I noticed here. So, it's a very good representation of the research that Julie is doing. It can, connect to the research that's going on back at home. Oh, oh.
All right, so if it's not too pixelated, we're gonna start our tour of the field site so we can show you what all of this instrumentation is actually doing and how they all relate to each other. and we're gonna try to time this perfectly to go off with our chambers. They already went off.
It's too far.
Okay, well, we apparently we did time it perfectly, and I missed the memo while I was talking. Oh, we are having malfunctions. Okay. So we're gonna talk about them anyway, and I'm sorry they won't go off. So this is Kai. Kai, do you want to introduce yourself?
Yeah, so my name is Kai Luna, and I work for the Woodwell Climate Research. Oh, sorry. Hello, my name is Kai Luna, and I work for Woodwell Climate Research Center, and I'm helping out here on this project and focusing on greenhouse gas emissions. So what you might have seen here, that what kind of looks like cheese domes, are automated gas samplers. So we have an instrument in that gray box. If you, yeah, there's an instrument that measures the gas. And here, this cheese dome, it's set on a timer. So they will go off and then close here and measure the neck ecosystem exchange of CO2, but also measure methane, which is another common greenhouse gas in these kind of wetland environments. And as Julia mentioned before, we have this gradient of different degradation states, and these transects or these chambers are capturing each of these coarse degradation states. And the greenhouse gas emissions from these transects give kind of a good fingerprint on how these different degradation states and how the soils gets affected, and how climate-induced warming change activity, both plants and microbes, and they give away carbon, different types of carbon emissions. So that's kind of what we're trying to capture with this setup. Yeah.
And one additional thing, you see all of this tubing across the tundra. So we have to, this is all over wires. And we have to protect all of our wires from animals.
You can, if you look here, come here.
Really?
Foxes.
To nibble?
They love to make nests here. So that's a big issue, that they gnaw and munch on our cables.
And then along with each chamber, we also are measuring soil moisture and soil temperature right alongside each of these chambers to have measurements at the same time. So now we're going to transition. Oh, you have a question. Okay.
Okay, so a lot of the students were at home were asking some questions for the scientists. So Kai, I'm going to ask you, what is your favorite place to do research other than right here?
Right here, my other favorite place to do research. That's a good question. Yeah, I don't know. I really like this. Yeah, I really like to be out in these kind of odd environments, because when else would you be able to see these kind of environments? But I worked a lot in Alaska, but also Fennoscandia. So northern Sweden and northern Norway is also very pretty places to be able to work. So I would probably say that.
Thank you.
Yeah.
All right, let's go to our next station.
And on your way to that next spot, everything's been sounding great, but there was a moment when you cut out. And so what is nibbling on the cables?
Oh, the foxes and the lemmings. They just love that extra little crunch that they get from the cables. So we're always protecting and wrapping up our cables to stop those foxes and lemmings from biting our cables and damaging our sensors.
And so the hole that we saw was a lemming.
That was for a lemming hole.
Great. Thank you.
Yeah, they kind of look like hamsters. They're really, I love hamsters. They're really cute. If we see any, we'll see if we can show you guys. They're running around here somewhere. Um, but yeah, I was going to talk a little bit more about the changes in vegetation. Before I do that, Julia reminded me I should introduce myself. My name's Alina Sphera. I'm a postdoctoral researcher at the Woods Hole Oceanographic Institution. So I work with Julia really closely to study the kind of physical, the impacts on the physical processes that are happening here on the coast. And one of the really interesting things about this project is it's a cool way to understand how the biological things, the ecosystem is affecting the physical processes and vice versa. So there's a lot of interactions here. And one of them is the impact on vegetation cover on the physical processes. So I was going to demonstrate how the data that we're collecting to kind of characterize or understand the vegetation cover. And so here I have, sorry, the mosquitoes are swarming right now. I've got O positive, you know, they love me. So I have a hyperspectral instrument here. And so it's kind of like a camera, but instead of taking an image with lots of different pixels, it takes a small area on the ground and has kind of one reflectance value, or one kind of the amount of light that's being reflected off the surface of the ground. And so I think I can do it with my, so this is a handheld instrument, which is really cool. So I can just kind of shoot the camera and get images or get spectra. So I'm going to take one here of this relatively healthy area, and then we'll be able to see the kind of peaks in the parts of the electromagnetic spectrum, or the different wavelengths of visible and non-visible light. And so we'll see if you can see the spectrum, maybe not. But it has this kind of peak here. This is near the green and red edge of the spectrum. So this is reflecting back a lot of green light here. So we know that site has a little bit more vegetation, and we can understand things about the vegetation condition, how healthy they are and how well they're doing. And then I have this kind of brown patch here that I'll take a spectrum of, hopefully. Okay, scan complete. Let's see. Oh my gosh. And this one's basically flat. So you can see all of that reflectance or light that we were getting reflected off the surface in the green and the red edge area is now much less and much flatter. And so we can take these really specific data, these really specific numbers about the colors reflecting off the surface, and characterize the condition of the vegetation. And then we can scale up and compare the data we're getting on the ground to things like satellite images or remotely captured data. And so this allows us to kind of take the data from our small field site and understand much larger regions. And I think Julia is going to talk a little bit more about the physical processes next. So that's my spiel. Okay, perfect.
Ask you a question. Okay, so Alina, how did you get into Arctic research? What was the driver for you?
Yeah, that's a great question. I think a lot of people, I think, in science fall into subjects serendipitously. And that was kind of the case for me. I loved coastal environments. I really liked like wetlands. And so I got the opportunity to start studying in the Arctic. And what really drew me to it is these environments are warming faster than anywhere else on the planet, and they're changing really, really quickly. And because they're so remote and hard to study, there's a lot of data and information that we're missing. And so that really motivates me to kind of continue to push the to expand our knowledge and get new information about these environments that are changing really quickly due to climate change. Yeah, we're going to fill in the gaps.
All right.
Thanks.
Let's go to our next scientist.
All right. Okay. You look great.
Okay. And I just want to highlight in terms of how quickly these environments are changing. This is our third field season and our last field season on this project. And even in those 3 years, this system we've seen change from the vegetation to the sedimentation. So I don't know if any of you can sort of spot this, but last fall we had one of the biggest storms that we've captured. And this is the so this actually used to be a healthy site right up here in green vegetation. And now it was inundated last fall, and the pore water, or the water under the subsurface, is showing that it was inundated with saltier water. And you can also see that flooding pushed in all this new sediment that was not here, even just last fall. But what I want to bring us back to is this question of the physical changes. So Alina showed you how the vegetation is changing on the surface and how we can monitor that with different spectra, but we actually are seeing changes in the subsurface. So the vegetation, as you can imagine, has an impact on the ground temperatures beneath the surface, right? So when you have really, really thick vegetation, like we see in the healthy tundra, it actually serves as an insulator of the ground. And when you have no vegetation, those areas are much more exposed to the atmospheric air temperature fluctuations. So they get both warmer and colder. And so to monitor these different aspects, we have these monitoring wells. So these are just glorified PVC pipes. At the bottom, there's a bunch of teeny tiny slits so water can flow through the well. In each of these wells, I think we have a logger in this one. Actually,
It's frozen.
It's frozen in, so we'll hop over to a different logger. We can find one that's not frozen in. Actually, that's a great example of below us. Everywhere below us is what we call permafrost. So this is ground that is frozen for 2 or more consecutive years. And so we're working in this really narrow zone, what we call the active layer, that is from the top of the permafrost, which is depending on the area, between 30 centimeter, a foot to a meter deep. And one way we can also monitor the temperatures in the subsurface are through these little instruments. These are multi-depth temperature probes. So in that active layer, right above the permafrost, we're monitoring the ground temperature. We have these in along this transect to really capture the seasonal variability and the spatial changes in the soil temperature above the permafrost. And so some of the interesting things that we've been seeing are what we were just talking about, that we have much deeper thaw depths. There's no vegetation. These soils in the degraded area get much warmer than the soils in the healthier tundra. And so we're seeing evidence of enhanced permafrost thaw in these areas that have saltwater inundation. You can think of a similar process of salting the road, right? You add salt to a system, the freezing temperature drops, your car doesn't skid out of control. The same thing is happening here. You add a bunch of salt, you have less vegetation. All these things act together to impact the subsurface. Alina, you have a bug on your neck biting you. The bugs are bad today, folks. All right, and so with that, we're gonna transition. Actually, do you have a question?
I do have a question. It's okay. The questions are safe questions. All right, Julia. So I have a lot of high school students that might be interested in pursuing a career similar to yours. What advice would you give a high school student just starting out?
Just starting out.
What should they get involved in, perhaps, before they make the decision? Since this is hard work.
Yeah, I think the first thing that came to mind is just like perseverance and persistence, right? As Alina said, you sort of serendipitously fall into these areas, but it's not easy, right? And I think we've all learned that you really need to push for what you really want to do, push for getting up here to the Arctic, right? It's not easy. But get experience and talk to people. I always have people emailing me, and it's one of my favorite things to do, just to chat with folks about my career and the different experiences and what I did in the past, you know, even during undergrad or during high school and before going to grad school. So get out there, talk to people.
Don't be afraid to ask the questions.
Ask the questions, and yeah,
Thank
helps
you.
inform decisions. Yeah.
All right. One
Right,
more
so now-
scientist.
Pass it off to the last aspect of our study.
Yeah. Hi, I'm Julia. I work at the Marine Biological Laboratory in Woods Hole, and I'm here helping out with the biogeochemistry aspect of this project. So if we walk this way, I'll show you a little bit more about what we do in conjunction with this project. I see you. So as Julia mentioned, when we get to this degraded state down here, the temperature changes, and one of the things that also increases is the thaw depth or the active layer. And so one thing we can do to combine our knowledge with Julia's knowledge and Kai's knowledge is actually use the chemistry of the water that's underneath us, so the water in between the pores of the soil. And the way we do that is, like Julia mentioned, she has those really deep wells or shallow wells that have little slits in the bottom, and we have a mini version here. Sorry, it's a little muddy. Oh yeah.
There we go.
There we go. Yeah. You got to swatch it.
You gotta swatch it. Okay. Yeah. Okay.
So, for example, hold on. Sorry. I need both hands for this. So one of the things that we do here with the chemistry is measure the water, the dissolved organic matter, the nutrients that come in, and how that changes with all of these flooding events. And so when the salt water comes in, and Julia mentioned this before, it's like road salt, it lowers the temperature, but like sodium and chloride, which are ions, and that makes up table salt, there's another ion, and the water is super high in sulfate. So as it comes in and percolates through the salt and through the soil, it actually releases nitrogen, and we can measure these changes. And so we actually stick this little straw down at certain depths. So we can do shallow measurements, we can do deep measurements, and pull up the water. So this acts as a straw. So like think about when you're sipping and you create pressure to pull up the water. So the three-way stopcock, and you pull. Oh, sorry. So we are creating a vacuum with this straw-like thing. So I'm gonna pull up the syringe, close the vacuum, release the air, and continue to do this until voila, we get water. And so typically we'll like flush this a few times because that's super dirty water. You don't want to dirty water. Yes. And so once I have like a syringe full right here, one of the first things we do is test the salinity of the water. And so we have a little handy device right here.
Should be sponsored.
Yeah, Myron, please sponsor us. Yeah. And as the true biogeochemist I am, I'm going to rinse it 3 times because some arbitrary number someone decided on years ago.
No, it's research.
Okay, and then we're going to fill. So we have a pH sensor and an oxidation reduction potential sensor, and then we have a conductivity sensor, which is what we translate to the saltiness of water, and a temperature sensor as well. So I'm going to fill up both of these sensors, and we're going to hit the conductivity button. And whoa, okay, so I don't know if you can see that, but it says 11.9, 11.60 millisiemens, which translates to about 12,000 microsiemens, and full strength seawater is about 50,000 microsiemens. So it's about a quarter of the salinity of salt water. Yeah. So what's coming in and what's percolating the ground and what's affecting the tundra here is salty, and you know up there it's fresher, and
Like 0 to 5.
yes, salt fresh water could be anywhere from like 0 to 200, 500 microsiemens. So this is really salty. But
Yeah, so at different depths, we can capture the salinity changes and also measure how the chemistry is changing as well. And yeah.
Okay, you ready for your question?
I am ready for my
Okay.
question.
Your question
I
is,
didn't run away from you.
no, that's okay. What is the hardest part of your job, and what is the most fun part of your job?
That's a good question. I'll start with the easy one. The most
Okay.
fun part,
Let's do that.
other than being somewhere so hard to get to, and I mean, I get to brag about this as my job and my life. Like, who gets to do this? Us. It's so cool. Is honestly the team members. I love collaborative projects and getting to work on a project like this and some other projects. It really gives you perspective for all these different things going on that make a coastal ecosystem so unique and hard to capture. The hardest part, probably getting up here. We had a lot of difficulties this time on some flight cancellations and long twice.
No,
Three times.
Get
Yes.
back to Anchorage.
So yeah, you can tell the weather's not so great here. But yeah, and the difficult field conditions, but that's what makes it worth it. Thank you. I'm gonna pass this back to the other Julia, JG.
Oh, okay. This one, so
All right. So I think at this point, that's the majority of our field tour. Hopefully you get a little better idea of how, changing storm dynamics and higher sea level and changing climate is impacting these coastal tundra environments. We're really just starting to, scratch the surface of these impacts. But that's why we're here with lots of instruments and continuing to do science. So I think we're happy to answer any questions, and
sure.
whether it's for the team or for Lauren and her experience here as an educator, we're ready for them.
Oh, great. Thank you all. Thanks so much for sprinkling in some questions from students, your students, Lauren, as well. And just for folks viewing at home, there was some cutting out, but they had mentioned about traveling being challenging. And so the part that cut out was that they got rerouted back to Anchorage at least 3 times, they said. So it took a while. That was due to weather, and then they had some flight cancellations too. Otherwise, the connectivity was pretty good. We had some pixelated views, but it was great. We could hear you all pretty well throughout. We did get some questions coming in ahead of time. We have Aria, she is 10 and she wanted to know what animals have you seen and what was the most interesting thing that you saw?
So what animals is this? Can you hear me? Okay. So hi, Aria. So let's see. The very first animal that we saw was caribou. They're everywhere. We saw mostly, by themselves, but we saw some mamas and babies. We saw some Arctic fox. We saw red fox. We saw lemmings. The birds, the plovers, the geese are all over. I think that my favorite is the caribou. I collected some caribou fur. We can take a look at that later.
Does anyone else from the team have a favorite, most interesting thing that they saw this trip?
I have a funny thing.
Oh, go for it.
So, since these coastal wetlands are also, one of the main breeding grounds for a lot of migratory birds, geese, but also a lot of shorebirds. So again, we see a lot of geese with ducklings and things like that, and the foxes are out preying on these. And one thing that the foxes do also before the eggs hatch is they go and steal the eggs, and then they catch them in different places. So as we were working out to one of our field sites the other day, I found I could see something white just protruding a little bit off the ground, and I dug a little bit, and sure enough, there was a hidden goose egg. So I thought that's always fun when you see things like that. Yeah.
Nice.
Yeah.
We have a question of For Elena, you talked about the
Oh,
reflectance of the vegetation and
sure.
um and this bigger picture concept. So what is this
Yeah.
bigger picture that we're learning from this data? Is it maybe like albedo effect or something else?
Yeah, one of the things that we're really interested in this project is we have this kind of one field site where we've seen this phenomenon and we've observed it, and now we want to see what other parts of the coast along the north slope of Alaska might be affected by similar things. And so we're using satellite imagery to try to detect the amount of saltwater intrusion affected areas or like coastal marsh areas there might be across this big area. And so we're taking the data here and understanding like what it looks like and what the spectral properties are so that we can detect it from satellite imagery and hopefully start mapping out the impact. And then what's really exciting about the work here is we know how much greenhouse gases could be coming in and out of these areas. And so we can kind of take those observations and understand on a larger scale. Once we have the area that's affected, we can scale up those biogeochemical measurements as well.
Very cool. Okay, nice. So you can
Yeah, I'm super
determine
excited about that.
so you can determine other locations that might have
Yeah,
undergoing similar effects without having to try to travel to those locations and see
yeah,
it.
yeah, that's right.
Great. Awesome. Let's see. Oh, Julia, you had mentioned like polygon, I think, a few times. And so what is a polygon? What do you mean by polygon?
Yeah, that's a great question. So the as I mentioned, this whole area is underlain by permafrost, and these areas, as that frozen ground, starts to thaw, there's what develops called ice wedges. And so um, they. Oh, are we moving? Gonna point out. So an ice wedge might be somewhere like in this trough, and so as the ground is thawing, it thaws different rates versus where you have this ice wedge formation rather than areas without the ice formation underneath. And so that dynamic actually creates these different types of surface features in the landscape. And so you have what we're standing on is a high center polygon. So that means that the center of the polygon is actually higher than what we call this trough network, which is the area that's underlain by polygons or by ice wedges. But then if you move further in the tundra, those are more like flat center. So there's no big hump in the center. And sometimes you even get low center polygons. And so all these different features are different permafrost degradation states that are expressed in this surficial landscape.
Okay, nice. Thank you.
Oh,
Oh no.
I think that.
Yeah.
You want to hold it?
Yeah. You want me to just
Let's see. We have another question. How do you weave all of these measurements together, and what picture are they creating for you of the change in this environment?
oh, that is the ultimate question. That's what we spend all our time thinking about. But I can tell you what we hope and what we plan. But really, how they weave together um, is what we go back to the office and study and do data analysis and develop numeric models to better understand. But the hope is we have all this information about the subsurface water, so how it moves, how it exchanges with the coastal ocean, the chemistry, and we have that in these different areas that provide almost a space for time picture. And So the bigger plans are right relating what we see in changes in the subsurface water and temperature to what we're seeing in the surface vegetation and the greenhouse gas fluxes. And that's why all of these measurements are co-located. But how they're going to come together and exactly how this site is different from that is still what we're doing back in the office and relating together. And so that is the big push for this last year of this 3-year project, is to pull everything together. One thing I can say is that Alina's done is already start to pull the changes in the pore water salinity to the temperature. So I talked a bit about that work and how those interact. So how we see deeper thaw depths and warmer temperatures in areas of higher salinity. So that's one way we're pulling, geophysical data with hydrogeological data and hydrological data and, temperature, thermal data. And as the project goes on, we'll pull in the biogeochemistry, we'll pull in the greenhouse gas fluxes, and the goal is to create like a really clear picture of this coastal degradation.
Great, thanks. So, yeah, folks, this is very cutting edge science. We don't quite know the answer
like,
yet, and that will be coming soon. And then we have time. Yeah. We have time for one last question. How about for Lauren? Or yeah, so what have you learned in the field that you can bring back to your students?
For the students. So I think the most important thing that I've learned here is how important it is to work together with the team. And that perseverance really is, key to learning. Asking questions constantly and not feeling embarrassed if you don't understand something, to just repeatedly ask until you do understand it. I think that's really important thing. That's a lot of times students feel like embarrassed to like ask those questions, but it's so important. In terms of science education, I think the collaborative community that has been established here is really important for other science teachers to understand at home, that it's not just science teacher by themselves. It takes a village of people to really drive education, and the more collaborative effort that educators put together is really going to drive science education further. As we're kind of in this time where there's a lot of things that are changing, working together as a cohesive team of support is really, really important. I love this team.
Well, that's great advice to really like continue to ask questions and foster that curiosity. That's great. Thank
Oh, I
you.
have one more thing for teachers.
Yeah.
You don't need to do something as big as what I was privileged enough to do. There's so many things in your local areas that you can dive right in. Do something that inspires you, because if you're an inspired person, then you're going to bring that inspiration back into your classroom. There's so many opportunities. Don't forget that why you started to be a science teacher in the first place, because you love science. Get back in, do the science. The science is a lot of fun. Sorry, forgot that.
No, that's great too. That's a nice reminder to all the teachers out there that might be watching. Thank you. And thank you both, Julia, Lauren, everyone else on the team. Thank you so much for your time and answering our questions and really showing us the amazing, cool work that you're doing up there. All right, I am going to go back to sharing my screen again. We hope for the field team that the rest of the field work goes well and that your travels home are smooth and uneventful.
We do.
Good warm wishes our way. Today is going to be our warm day.
60 degrees, what?
All right, and to all our viewers, thank you for joining us and sending in some insightful questions. There are many ways to engage with Polar Steam. You can subscribe to our YouTube channel and follow us on social media at Polar Steam Team. To see our blog, educational resources, and program information, please check out our website. A reminder that a recording of this live stream will be posted on our YouTube channel. And thank you for tuning in to Polar Steam's Cool Connections today, and we hope to see you at our next one. Thank you.
Bye. Thanks, everyone.
Don't hang up on them. I think they want to talk to us after.